Hey guys. So we had this picture the other day of all the particles in the Standard Model. So these are all the particles that make up atoms and galaxies and light and dogs and coffee mugs and everything else that we can see in the universe. So here is a diagram of how these particles interact with each other. So for example, quarks could interact with gluons, quarks could interact with Z bosons, with photons. Quarks cannot interact with leptons, but quarks can indirectly interact with a lepton. So a quark could interact with a photon. That photon could then interact with some of these leptons over here. So the particles of the Standard Model can interact with some particles, but cannot necessarily interact with all the particles of the Standard Model. And that is except through the gravitational interaction. So a quark has mass, a lepton has mass. All these particles will, to some degree or other, curve the background space-time on which physics is taking place. So all of these particles can interact with each other through gravity. Now we could imagine, how do we know these are all the particles in existence? What if there are other particles that do not interact with any of these Standard Model particles on the screen right now? And the answer to that is ultimately we don't know. There might be other particles that interact with the Standard Model particles. So if I were to include a diagram of some of these particles, it might look something like this. So here I drew 4 particles. Particle 4 does not interact with anything. Particles x1, x2, x3, they have some interactions between each other, but none of these particles that I called x interact with any of the particles in the Standard Model. So the only way we would possibly be able to know of the existence of these X particles in the way I drew this diagram is to observe their gravitational effect on objects. So the first evidence for the existence of dark matter came by measuring the rotation rate of other galaxies. Now, we could infer that if all the matter in a galaxy were the luminous matter, in other words, all the matter in a galaxy were the stars and the clouds of gas and dust and all that other stuff, then we would expect there to be a certain speed at which stars in the galaxy orbit the center of the galaxy. In the 60s and 70s, Vera Rubin and her advisor Ken Ford discovered that galaxies seem to rotate much faster than they should. In other words, if the galaxies were rotating this fast, we would expect that stars in the galaxy should just be ejected and flung out into space because this galaxy is rotating too fast. Unless there was a lot more matter in that galaxy than what we could see. If there's a lot more matter in that galaxy, then the galaxy will have a stronger gravitational pull and be able to hold on to those stars and prevent them from being flung out into space. So if we go out from the center of the galaxy to greater and greater distances, we would expect the speed of the stars to gradually get slower and slower, but that isn't what was observed. What was observed was the speed of the stars is pretty much increasing and getting bigger and bigger, and we would expect these stars way out here to be flung off into interstellar space. So this was the first very strong evidence of the existence of dark matter. In the 1930s, the astronomer Zwicky measured the rate at which galaxies are orbiting in a galaxy cluster. And he found the rate at which galaxies were moving around seemed to suggest there was a lot of invisible material in that galaxy cluster. And that was the first evidence for the existence of dark matter, but this was the first very strong, convincing evidence that there is some unseen material inside that galaxy. So a galaxy itself is going to be surrounded by a huge halo of dark matter. So the galaxy we could see with a telescope, with a really good telescope, is only going to be about this big. But there's a giant halo of dark matter, much bigger than the galaxy surrounding it. So this halo is much larger than the galaxy, and the extra mass from this halo is what prevents the stars that are orbiting the galaxy from flying off into intergalactic space. So before I talk more about dark matter, I want to talk about the connection between light and electric charge. A photon is just a particle of light. Now, we said before that light comes in many colors. You have blue and orange and purple and red. But in addition to the colors we could see, there is also ultraviolet, X-rays, there is infrared and radio waves. Literally, infrared and radio are just colors of light that our eyes, due to the biology of how our eyes work, our eyes are not able to see the color of radio. But radio is literally just another color of light. Now, any object that contains electric charge will be able to interact with a photon. A photon is a quanta or a unit of electromagnetic field. So anything that has charge can interact with a photon. So for example, a W boson contains electric charge, so a W boson can directly connect with a photon. The quarks all contain electric charge, so the quarks can directly interact with the photon. And the electron, the muon, and the tau are charged particles. They contain all -1 charge. So the electron, the muon, the tau all are able to directly interact with a photon. What about protons? We talked about those having electric charge before. Protons are actually made of quarks, so protons interact with photons because quarks have electric charge. Now, on the other hand, particles that do not contain electric charge, such as the Higgs or the Z boson or the gluon, a particle that contains no electric charge cannot interact with light. So, for example, if I had a cloud of gluons and I were to shine a light through that really thick cloud of gluons, the light would travel right through the cloud of gluons because gluons do not interact with photons, so the photons will not see the gluons at all. They'll travel right through them as though they were not there at all. Now, dark matter is a type of particle that does not interact with anything in the standard model, in the standard picture of how dark matter behaves. There are some hypothetical dark matter scenarios where maybe dark matter has a very weak interaction with a W or a Z boson, but I'm ignoring that. The standard picture of dark matter is made up of particles that have no interaction with the particles of the standard model. So the particles that make up people and dogs and coffee mugs and footballs, those objects are all made of atoms, and atoms have no way to interact with dark matter. Now, dark matter, as far as we know, it might just be one type of dark matter particle, or maybe there are several types of dark matter particles. Maybe dark matter particles do not interact with anything at all. Maybe within the dark matter particles, they have some interactions between them. So here I have a picture where hypothetically dark matter X1 interacts with dark matter X2 and interacts with dark matter X3. And dark matter particle X3 interacts with other dark matter particles X3 and will interact with dark matter particle X1, but dark matter particle X3 cannot directly interact with dark matter particle X2. And dark matter particle X4 over here doesn't interact with anything whatsoever. So shown above, I just completely made up a picture where I have 4 types of dark matter particles, and I threw in a few interactions among them to make this picture a bit more interesting. I have there's no scientific basis for this picture. I just wanted to demonstrate the fact that there could be particles out there that do not interact with any particles in the standard model that we know of. Now, there is no interaction with particles that make up atoms and things that we work with other than through the gravitational interaction. Because we said gravity is really a deformation of the background on which physics takes place. So there are a bunch of interactions, but all particles will, to some degree or other, curve the background on which physics takes place. And if the background space-time is curved, then we have a gravitational interaction. And the background space-time should curve similarly for any type of particle. So Even though we cannot directly observe dark matter particles because we can't put them in a particle collider and try to bounce photons off them to learn their properties, we could still infer the existence of dark matter, and if we're really clever, maybe even figure out some clues as to dark matter's properties by observing dark matter's gravitational effects on other objects. So here we have a picture of the bullet cluster. Long ago in the universe, there was a collision between two clusters of galaxies, and in this collision, you have a bunch of galaxies that are kind of like point particles in their cluster, and then between the galaxies there is intergalactic gas, and this gas is just made up of normal atoms. Now in this picture, the galaxies are shown in white, for the most part in their natural color. The hot gas that was between the galaxies in the cluster is shown in pink, and then the location of dark matter is shown in blue. So originally one galaxy cluster was over here, one galaxy cluster was over here, and then they both were approaching each other, they collided. And what happened was, because the hot gas fills up a big region of space, the hot gas collided, and then the hot gas kind of stayed in place. Meanwhile, the galaxies are like point particles, so the galaxies pass by each other. They didn't really collide that much. And what about the dark matter between the galaxies? Well, the dark matter doesn't really seem to interact with anything. So the dark matter just passed on through, and so the hot gas between the galaxies was stripped away when it collided with hot gas in the other cluster. But the dark matter and the galaxies just continued on through as though, and were not really significantly affected by the collision. Now, we could know the location of dark matter by looking at the amount of gravitational lensing in the background. We talked about gravitational lensing previously in 112 and 113. So that's just, gravitational lensing is a deformation of the shapes of really distant objects due to a lot of mass in the foreground. So this picture is a very strong evidence for the existence of dark matter, because what we had is we see galaxies and we see other unseen matter that is warping the background space-time, but we have nothing there. Now this picture was color-coded. The hot gas actually emits in X-rays, so pink was added to show off where it was. And like I said, what you do is, to find the location of dark matter, you would look at the galaxies in the background. You look for the shape of the galaxies to be distorted a little bit. And where you see this distortion, you put some blue there to show this is the location of the dark matter. Now, we should be able to say a few properties about dark matter. We expect dark matter to be electrically neutral. If dark matter has no charge, it should not be able to interact with photons. Also, we expect dark matter to be stable. If dark matter decays into other particles, it should have a half-life longer than the current age of the universe, because we don't see evidence of dark matter significantly changing its properties between distant galaxies that we see from long ago versus nearby galaxies in the present-day universe. And also, dark matter should be collecting inside the sun and inside the Earth, because if you have an object the mass of a rock, or if you have some dark matter hitting the sun, well, the sun has a really strong gravitational field. And because of that, if dark matter is going to be attracted towards the sun if it's moving slowly, then dark matter should be collecting inside the sun. It gets trapped by the sun's gravity and collecting there. So, in conclusion, dark matter is unknown matter. Now, dark matter and dark energy are not the same thing. While we don't know what dark matter is, dark matter does seem to behave like normal matter. In other words, dark matter dilutes in a manner very similar to how normal matter dilutes as the universe expands. So it dilutes just like cold, gas, and dust. Dark energy does not dilute in this manner. Dark energy dilutes very differently as the universe expands. And there are some proposed explanations of what dark matter might be, but at present, these are all speculative.